A construction crew in Seonggan recently finished installing what looked like standard architectural glass on the south facade of a government pilot building. It was not standard. Each panel was generating electricity. The building's grid draw dropped by 40% compared to an equivalent structure next door. Let me be precise about what that number means. A 40% reduction in grid draw from the facade glass alone, not from rooftop solar, not from a separate generation system bolted on afterward, but from the windows themselves, represents a performance figure that the International Energy Agency's own BIPV roadmap had not projected until 2030. If you find that hard to believe, you are in good company. The engineers who reviewed the initial data asked for a second independent verification before they published it. Stay with me through what follows and subscribe before you do, because the honest explanation of how this works requires dismantling several things you probably think you know about solar energy. For every building that has gone up in the last half-century, the glass was always the passive part. It emitted light, shed rain, and held the wind back. That was the complete list of things glass was allowed to do. The physics of conventional solar cells, opaque crystalline silicon absorbing photons and converting them to current, made the idea of a transparent, power-generating window feel like a category error. Not a hard problem, a wrong problem. Something that violated the internal logic of both materials simultaneously. That logic held for a long time, and it held for good reason. The photovoltaic effect requires a semiconductor to capture photons. The more photons a semiconductor captures, the more current it produces. But capturing photons means absorbing them, and absorbing them means the material goes dark. The window stops being a window. Every serious attempt to combine transparency with solar generation ran into this wall, and the wall was not an engineering failure. It was a straightforward consequence of physics. You could have a solar cell or you could have a window. The field consensus, held by the best laboratories in the world, was that you could not have both at meaningful efficiency. The institutions that defined that consensus were not guessing. The National Renewable Energy Laboratory in Colorado, the Fraunhofer Institute for Solar Energy Systems in Freiburg, and the MIT Energy Initiative spent the better part of 2 decades mapping the trade-off with precision. By the late 2000s, the established benchmark for any semi-transparent photovoltaic system, meaning a solar cell thin enough and sparse enough to let some light through, sat at around 8% power conversion efficiency under standard test conditions. 8%. A conventional rooftop silicon panel was hitting 20% to 22% by the same period. The gap between what you could see through and what could actually generate power had been measured, published, and accepted as a structural feature of the technology, not a temporary limitation waiting to be engineered away. The cost argument reinforced the physics argument. Building integrated photovoltaic glass in that era ran between $400 and $900 per square meter installed, against conventional curtain wall glass at roughly $80 to $120. At 8% efficiency and a cost premium of 4 to 8 times, the payback period on a commercial building facade stretched to 25 or 40 years. Most commercial leases run 10. No developer with a functioning spreadsheet was going to specify it. Architects designing curtain wall systems, the continuous glass skins that define the skyline of every major city, optimized for visible light transmittance, thermal performance, and structural load. Adding a marginal and expensive solar function that compromised all 3 was not a serious conversation in most design offices. The ceiling had a name, a number, and a price tag. It had been set by credible institutions using rigorous methodology, and it had been stable long enough that the industry had stopped actively trying to break it. What changed was not a laboratory result. It was an announcement from a manufacturer. The announcement came quietly. No keynote, no press conference. A product specification sheet from a Chinese manufacturer claiming power conversion efficiency above 12% for a commercially produced semi-transparent photovoltaic glass panel, alongside a visible light transmittance figure that met standard architectural glazing codes. The company was LONGi Green Energy, already the largest silicon solar module manufacturer on Earth by output. The product line was their BIPV glass division. The number they published was not a laboratory result under optimized conditions. It was a commercial specification for a product they were prepared to ship. The reaction from the international research community was immediate and consistent. Fraunhofer, the firm's SE, noted that efficiency figures for semi-transparent PV systems are highly sensitive to test conditions. that a claimed 12% under real-world installed performance would require a cell architecture that had not yet been demonstrated at manufacturing scale. The IEA's Photovoltaic Power Systems program flagged the claim as unverified under IEC standard conditions. Trade publications covering the solar industry characterized the announcement as aspirational. The specific technical objection was precise: depositing a functional tandem cell architecture onto float glass at production line speed while maintaining both the optical consistency required for architectural glazing and the electrical uniformity required for reliable power output had not been done. The claim implied a manufacturing process that did not publicly exist. They said the same thing about CATL's lithium iron phosphate battery density claims in 2020. The global battery industry is now built on that chemistry. The dismissal followed a pattern that the history of Chinese industrial scaling had already written several times over. What the external commentary missed was what the announcement actually represented. Not a prototype result, not a research paper, but the output specification of a vertically integrated manufacturing operation that had been running quietly for the better part of a decade. LONGi had not started with the glass, they had started with the cell. Their heterojunction silicon technology, developed through years of incremental refinement on standard module lines, had already pushed single-cell efficiency past 26% in laboratory conditions, a world record at the time. The BIPV glass program was the application of that cell chemistry to a new substrate at a company that already owned the float glass supply chain relationships, the deposition equipment expertise, and the domestic construction market volume needed to absorb the cost of learning a new process at scale. That combination, cell chemistry, manufacturing infrastructure, and a home market large enough to be its own proving ground, was not something any Western competitor had assembled. The dismissal treated the claim as a laboratory boast. It was a manufacturing declaration. But what the specification sheet did not explain was how they had actually solved the deposition problem. That answer required looking inside the factory. The problem at the center of BIPV glass manufacturing is not chemistry. The chemistry of heterojunction silicon cells had been understood for years. The problem is speed. A float glass production line moves continuously. Molten glass flows onto a bath of liquid tin, spreads to a uniform thickness, and travels down a carefully temperature-controlled annealing layer at a rate measured in meters per minute. The entire process is optimized for one thing: producing optically flawless glass at the lowest possible cost per square meter. Stopping that line, or slowing it, to apply a photovoltaic cell layer using conventional batch sputtering processes, the method used in most thin-film solar manufacturing, would eliminate the cost advantage that makes float glass the default building material for every commercial project on Earth. You would be adding an expensive, time-consuming step to a process whose entire value proposition is that it never stops. The conventional approach had tried to solve this by treating the glass and the cell as separate manufacturing steps. Produce the glass, cut it, move it to a separate facility, apply the cell layer in a controlled batch environment, then ship it back into the glazing supply chain. Every additional handling step added cost, added breakage risk, and added time. The result was a product that was technically functional and commercially uncompetitive. What LONGi's process engineering team developed was an atmospheric pressure chemical vapor deposition system, APCVD, designed to operate in line with the float glass line itself. Think of it not as painting a wall with a brush, one panel at a time, but as running the glass through a precision fog chamber at the exact speed the glass is already moving. The chemical precursors for the cell layers are introduced as a controlled vapor at specific temperature zones along the existing production path. The glass does not stop. The process does not interrupt. The cell chemistry bonds to the surface uniformly because the deposition environment moves at the same rate as the substrate passing through it. At LONGi's Xi'an pilot facility, the Inline APCVD process demonstrated consistent cell deposition at production line speeds exceeding 8 meters per minute, with power conversion efficiency measured at 13.1% under IEC 61853 standard test conditions across a full production run. Not a selected sample, a full run. The optical consistency across the coated surface met GB/T architectural glazing standards for commercial curtain wall applications. This is not a coating applied to a window, this is a window grown around a power cell. The deposition problem was solved. But solving deposition at speed created a second problem that the first solution made worse. and it lived in the part of the light spectrum that human eyes actually use. The tandem cell architecture that made inline deposition viable absorbed photons across a broad spectrum. That was the point. A perovskite top cell capturing high-energy photons, a heterojunction silicon bottom cell capturing the remainder, the two layers working in sequence to extract current from as much of the incoming light as possible. The problem was that the visible spectrum, the wavelengths between roughly 380 and 700 nanometers that human vision runs on, sat squarely inside the absorption range of the perovskite layer. The glass that came off the production line was tinted. Not dramatically, not opaquely, but enough. Visible light transmittance measured between 20% and 28% on early production samples. That figure failed commercial daylighting codes in most major building markets. It also failed the subjective threshold below which building occupants reliably report dissatisfaction with their working environment. The apparent contradiction was clean and uncomfortable. The more efficiently the cell absorbed light, the darker the glass became. The more transparent the glass, the less current it produced. Every adjustment in one direction degraded performance in the other. The conventional response, accepted across the industry, was to pick a point on the trade-off curve and live with it. Accept lower efficiency for usable transparency, or accept darker glass for meaningful power output. No manufacturer had escaped that curve. The solution that Longhi's materials team developed did not try to escape the curve. It changed what the cell was being asked to absorb. The innovation was a luminescent solar concentrator interlayer, a thin film embedded between the glass lights, formulated from cadmium-free zinc copper. Indium selenide quantum dots tuned to absorb in the near-infrared and ultraviolet bands, specifically the portions of the solar spectrum that human vision does not use and that building occupants cannot perceive. Instead of competing with the visible spectrum for the same photons, the interlayer intercepted the invisible portions, re-emitted them at wavelengths matched to the cell's peak absorption band, and directed them toward the cell layer via internal reflection. The visible spectrum passed through largely intact. TÜV Rheinland's Shanghai testing facility certified the combined system, inline deposited tandem cell plus LSC interlayer, at 14.2% power conversion efficiency alongside 43% visible light transmittance, both figures in the same document under IEC standard conditions on a commercially produced panel. It sounds like it should not work because it is asking two different layers to do two different jobs on the same substrate simultaneously. That is exactly why it does. The cell is not competing with the window anymore. They have been assigned different parts of the light, demonstrating that in a certified panel was one thing. Wiring thousands of those panels into a building that could actually use the power was an entirely different engineering problem. A single BIPV glass panel generating 14.2% efficiency across 43% visible light transmittance is a materials result. A 40-story commercial tower with 12,000 square meters of south, east, and west, facade, glazing. Every panel generating variable power output depending on its orientation, its shading profile, the angle of the sun, the ambient temperature, and the spectral composition of the light hitting it at any given second, is a network problem. And network problems at that scale do not solve themselves. The conventional building energy management system was not designed for this. BEMS architecture developed over decades around a simple model: fixed demand loads, lighting, HVAC, elevators, drawing from a stable grid supply. The control logic assumed that power flowed in one direction, from the grid into the building, and that the building's job was to manage consumption. Embedding 12,000 variable microgenerators into that model did not extend it. It broke it. A facade panel in direct noon sun on the south face produces maximum output at the same moment that a panel 2 meters away, partially shaded by a neighboring structure, produces almost nothing. Aggregating that variability without destabilizing the building's internal grid or sending unmanaged surplus back into the city network required a control architecture that conventional BEMS could not provide. The solution deployed in China's Zero Carbon Building Pilot Program, a priority designation under the 14th five-year plan targeting net zero energy performance in new commercial construction, embedded a distributed microinverter behind each individual panel. Each microinverter performs panel-level maximum power point tracking in real time, converting the panel's variable DC output to stable AC regardless of what adjacent panels are doing. Those microinverters feed into a building-level AI energy management layer that functions like a city traffic control system, except instead of routing vehicles, it is routing electrons. Second by second, it reads, which panels are producing what, cross-references the building's instantaneous load profile across HVAC, lighting, and vertical transport, and distributes generation output to the highest priority consumption nodes first, with grid export as the overflow valve. At the Jiangnan New Area Government Complex, designated as the program's primary pilot site, 8,400 square meters of BIPV facade glass were installed across 3 connected structures. Annual metered generation output came in at 1.26 million kilowatt hours. The building cluster's total annual energy demand was 2.9 million kilowatt hours. The facade glass alone was covering 43% of the load, from surfaces that, in a conventional building, would have contributed nothing beyond keeping the weather out. This is not solar panels on a building. This is a building that is a power plant. The combined system output was large enough that the program's oversight committee requested a second independent verification before releasing the figure. That verification produced a number with consequences well outside the construction industry. Here's the honest picture. The China Building Material Test and Certification Group, operating under CNAS accreditation, independently verified the Xiong'an pilot's metered annual output against the installed facade area and confirmed a normalized generation figure of 148 kilowatt hours per square meter per year under real-world operating conditions. Not standard test conditions, not laboratory simulations, but measured output from a functioning commercial installation over a full annual cycle. For a fully glazed 40-story commercial tower with 15,000 square meters of active facade area, that figure translates to approximately 2.2 million kilowatt hours per year. The average Chinese urban household consumes roughly 1,800 kilowatt hours annually. One building's glass skin, generating power as a secondary function of keeping the weather out, would cover the annual electricity consumption of more than 1,200 homes. The verified CO2 avoidance figure, calculated against the IEA's 2023 grid emissions intensity benchmark for Eastern China, was 1,040 tons per building per year. Now the trade-offs, because they are real and they matter. Current installed cost for the full BIPV glass system, panel, microinverter, AI management layer, runs approximately 45% to 60% above conventional high-performance curtain wall glazing at equivalent specification. That premium is compressive against the payback calculation, and at today's commercial electricity prices in most markets, the simple payback period remains in the range of 14 to 18 years for a standard commercial building. Efficiency degradation in the perovskite top cell layer is running at approximately 0.6% per year under accelerated weathering tests, faster than conventional crystalline silicon, which degrades at roughly 0.3% to 0.5% annually. The building code frameworks that would allow BIPV glass to be specified as a primary energy system, rather than an ancillary add-on, do not yet exist in the EU, the United States, or most Southeast Asian markets. These are not minor footnotes. They are the active constraints on deployment outside of China's own construction pipeline. And yet, the verified output figure exists. The independent certification exists. A functioning commercial installation across multiple connected structures has produced a normalized generation result that the IEA's own BIPV technology roadmap had not projected for commercial products until the end of this decade. Glass that generates electricity at architectural scale is not a research ambition anymore. It is a certified, installed, metered fact, and the question of what happens next does not belong to the engineers. It belongs to the institutions, the markets, and the governments trying to decide what to do about it. Buildings are responsible for 37% of global energy-related carbon dioxide emissions, according to the IEA's most recent building sector report. Not transportation, not heavy industry. Buildings. The standing stock of constructed floor area that heats, cools, lights, and ventilates itself around the clock in every city on Earth, using energy systems that were largely designed before climate targets existed. The building envelope, the roof, the facade, the glazing, is the single largest untapped surface for distributed generation in the built environment. It is also the surface that every serious net zero building standard, from the EU's Nearly Zero Energy Building Directive to Singapore's Green Mark Platinum Framework, has identified as the next mandatory performance frontier. The Xiong'an result landed directly into that context. The regions watching most closely are not the ones you might expect. The Middle East, where glass-dominant high-rise construction is accelerating across Riyadh, Dubai, and Doha at a pace that no other market currently matches, has the solar irradiance, the construction volume, and the national energy transition mandates to make BIPV glass commercially compelling at scale if the cost curve continues its current trajectory. Southeast Asia presents a similar case. Rapid urbanization, high solar resource, and a commercial construction pipeline growing faster than the grid infrastructure designed to serve it. Within the European Union, the revised Energy Performance of Buildings Directive, which requires all new commercial buildings to be equipped for solar energy generation from 2030 onward, has created a regulatory demand signal with no currently adequate domestic supply response. What adoption actually requires is not the patent. Patents are available. What adoption requires is the full vertical stack. Float glass manufacturing capacity, inline cell deposition capability, quantum dot interlayer chemistry at production volume, microinverter supply chain integration, and an AI building management software layer mature enough to manage real-world installation variability. China spent approximately a decade assembling that stack, inside a domestic construction market large enough to absorb the learning curve cost of each component. No other country currently has all 5 layers operating at commercial scale simultaneously. The EU's BIPV action plan, published under the European Green Deal framework, explicitly acknowledged the Chinese manufacturing lead at the technology readiness level and identified no funded domestic program operating at equivalent scale in response. When Japan's Sharp and Sanyo led global solar module manufacturing in 2005, Chinese producers held less than 5% of world output. By 2023, that figure exceeded 80%. The BIPV glass transition is running approximately 15 years behind the module transition in its development curve. The module transition took 12 years to complete. The limit was never the physics. It was always the industrial system built around the physics. If you made it this far, you now understand more about building integrated photovoltaics than most people who write about the energy transition for a living. And what you understand is not primarily a story about glass or about solar cells or even about a single certified result from a pilot building in Xiong'an. What you understand is that the transparency-efficiency trade-off, the wall that defined the field for 30 years, was never a permanent physical constraint. It was a manufacturing integration problem. And manufacturing integration problems do not get solved in laboratories. They get solved by companies with the cell chemistry, the production infrastructure, and the home market scale to absorb the cost of solving them commercially. China had all 3. No other country currently has all 3 in the same place at the same time. The inline deposition process made the cell viable at production speed. The luminescent solar concentrator interlayer separated the visible spectrum from the generation function. The distributed microinverter network and AI management layer turned 12,000 variable panels into a coordinated power system. And the certified metered result, 148 kilowatt-hours per square meter per year, independently verified on a functioning commercial installation, confirmed that the system works outside a laboratory in real weather across a full annual cycle. If that kind of analysis is useful to you, if understanding how these breakthroughs actually work, rather than just that they happened, is worth your time, then a like and a subscription are the most direct way to tell us to keep going. Hit the notification bell while you are there. We're going to keep following this story closely, and the next inflection point to watch is the first large-scale BIPV glass tender outside China. Because when that contract is awarded, the question of who can actually fulfill it at specification will answer itself very quickly. One question before you go, and I want your honest answer in the comments. I read every single one. Is building integrated photovoltaic glass the future of urban energy generation, or is distributed rooftop solar paired with battery storage still the more practical path for most of the world's cities? Both sides of that argument have real weight. I want to know where you land. See you in the next one.